OCR Chemistry A 6.2.3 ACD carbon-13 NMR spectroscopy. Using Chemistry Explained means participating by writing notes and completing the tasks with a pen on paper or on a tablet. Pause and replay the slides at the pace that suits you. Most importantly, when prompted, pause the lesson, thinking a problem through, taking your time, completing the task before continuing and correcting your work. We will start with some general principles of NMR, nuclear magnetic resonance. Atomic nuclei contain the nucleons, that is the protons and the neutrons. If there is an odd number of nucleons, the nucleus has significant spin. A spinning nucleus, as it is charged, generates a magnetic field, and this can be identified by the absorption of low energy radio waves. This is called nuclear magnetic resonance. Nuclei with significant spin are the hydrogen nucleus, carbon-13, and, for example, fluorine-19. Nuclei without spin, that is, they have even numbers of nucleons, carbon-12, and the isotope of hydrogen, deuterium, hydrogen-2. So the frequencies of radio waves absorbed are compared to a standard molecule, which we will identify in a later slide, and presented in a spectrum of absorption peaks or signals. Those signals have been shifted away from the standard, that is, they've got a chemical shift, and that's in parts per million. And you will see here from the OCR datasheet typical chemical shifts for particular carbon environments. So the chemical shift of an atom is altered by the groups or atoms to which it is then attached, called the chemical environment. And we can identify these particular environments through the shift values. Notice the chemical shifts increase from right to left. So we're increasing right to left. That's slightly unusual. Second point, if a carbon is close to an electronegative element, then the shift value is increased. Similarly, if the carbon is close to a multiple bond, for instance, a carbon double bond oxygen or a carbon-carbon double bond, that will also increase shift values. So how are these chemical shifts obtained? Well, you place a liquid sample in a tube, which then spins in a magnetic field. If the sample is solid, rather than a liquid, then it needs to first be dissolved in a solvent. But we have to have a solvent which will itself not interfere with the signals. So we use deuteriated solvents, that is, we use the isotope deuterium, H2, because of course having an even number of nucleons, it does not produce an NMR signal. How do we scale? Well, we use a reference material, tetramethylsilane. So here is tetramethylsilane, and you will see that the carbon environments are identical. So it's going to produce one signal, one absorption peak. Each carbon will contribute to that absorption peak, but it will have the same shift value. And it's agreed to calibrate the scale to 0 at the TMS, at the tetramethylsilane absorption. TMS is also non-toxic and chemically inert, so it doesn't interfere or change the nature of a compound that is dissolved in a solvent. So let's move on to look at some carbon-13 NMR. So carbon-13 spectra reveal two things about an organic molecule. The first is the number of different carbon environments, and we get that from the number of signals. And we can also, from the shift values, we can determine the type of the carbon environment. So let's look at an example, ethanol. Here is the carbon-13 spectrum for ethanol. Here is the molecule ethanol. We've got two carbon environments, two signals, two peaks. Pause. Can you attribute the peak to a carbon environment? Which of these two carbon environments is responsible for which of these two peaks? Pause, come back when you've thought about it and you're ready to hear my explanation. Okay, so I hope you've had a think. The carbon-oxygen environment, carbon single bond oxygen, is listed in, I'm looking at the data sheet to my left as I speak, 50 to 90. So that would account for the peak further to the left, what's called downfield. Then we have a peak between 0 and 50, and that would correspond to a carbon-carbon. So we're able to say, right, ethanol, two carbon environments, and we're able to attribute the peaks to the two different carbon environments and identify them as carbon-oxygen single bond or carbon-carbon. So here is cyclohexane. Pause the lesson and predict or sketch the carbon-13 spectrum that you would expect for cyclohexane. Pause, come back when you are ready. Okay, so I'm going to reveal. Cyclohexane, of course, has 6 carbons, but they're all in identical chemical environments. They're all chemically equivalent. So the term chemically equivalent means that the environment for the particular atom, the carbon atom, is identical. So we will say each of these 6 carbons are chemically equivalent, which means that whilst if there's only one chemical environment, we will only get one absorption peak. Each of the 6 carbons will contribute to it, but it will be at the same shift value. So we'll get one absorption peak, one carbon-13 signal, and that will correspond somewhere between 0 and 50, as this is a carbon-carbon environment. So let me give you another problem. Predict carbon-13 spectra, NMR spectra, for the carbonyl isomers propanone and propanal, and assign signals to each carbon environment. So for propanone, predict a carbon-13 NMR spectrum, and for propanal, the same. Sketch them out, think it through, have your reasoning, come back when you are ready to check against my ideas. Okay, so I'm going to reveal. So there is propanal. We've got 3 peaks. 1, 2, 3 different carbon environments, 3 peaks. The carbon double bond oxygen is in the region 160 to 220. And we have carbon-carbon bonds, carbon, 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 but this carbon is much closer to an electronegative element, so its shift value will be increased. Now, if we now look at propanone, well, these two carbons have an identical chemical environment. That is, they are chemical equivalents. That means we're only going to get two peaks. We've only got two different carbon environments. We've got the carbon double bond oxygen and the carbon-carbon. But these carbon atoms are in identical chemical environments. That is, they are chemically equivalent. So they will both contribute to this carbon-13 signal, but it will just be the one signal. This signal will correspond to the carbon double bond oxygen in the range 160 to 220. So we can confidently say that this is the spectrum for propanone, and this is the spectrum with 3 peaks for propanal. So here are some problems. Predict the number of peaks in the carbon-13 NMR spectra for pentane, butane, pentan-3-one and pentan-2-one. Think it through. Come back to check against my ideas when you are ready. Okay, so if we take pentane, start with pentane, we've got a CH3 group, and we can see that these two carbon environments are chemically equivalent. They are identical, as are these two chemical environments for these carbon atoms. So we've only got 1, 2, 3 different chemical environments, 3 peaks. Now if we look at butane, we'll see again these are chemically equivalent environments, and these are chemically equivalent environments, so we will have 2 peaks. Now if you need to pause before I go through pentan-2-one and pentan-3-one and rethink your ideas, please do so. Otherwise I'm going to proceed. So pentan-2-one, we've got our carbonyl group positioned here. So this carbon is at a different distance from the oxygen compared to this carbon. So there are no chemically equivalent carbons within that molecule. So we have 1, 2, 3, 4, 5 different chemical environments, and therefore 5 peaks. Whereas if we look at pentan-3-one, the carbon of the CH3 groups, well, they are chemically equivalent, are they not? These two are chemically equivalent, as are these. So this carbon and this carbon are the same distance from the oxygen of the carbonyl group, so they are chemically equivalent. So we only have 3 different chemical environments for the carbons, so 3 peaks, 3 signals for pentan-3-one. So if we consider aromatics such as benzene, here is our structural diagram for benzene, we're going to employ the same sort of thinking as we did for cyclohexane, in that each of the 6 carbon atoms have identical chemical environments. That is, they are chemically equivalent, and therefore they absorb at the same shift value. That is, there is one carbon environment, one type of carbon environment, and therefore there is one absorption signal. So each of these 6 carbons contribute to this absorption signal, but it's always at the same chemical shift value in the range 110 to 160. So let's consider other aromatics with multiple substitutions in the benzene ring. So how many carbon-13 NMR signals for each of the positional isomers of methylphenol? So we have 2-methylphenol, 3-methylphenol, and 4-methylphenol. How many carbon-13 signals for each of these positional isomers? Think it through, pause, come back when you have reached some conclusions, and listen to my explanations. Okay, so I'm going to reveal. We'll see that 2-methylphenol has 7 peaks. There are no chemically equivalent carbon environments. There's 1, 2, 3, 4, 5, 6, 7 different chemical environments for each carbon. They're all at different distances from the oxygen of the phenol group and the methyl group. So similarly here, we've got 7 peaks. 1, 2, 3, 4, 5, 6, 7 different environments. However, if we look at 4-methylphenol, we'll see that this position and these positions within the ring are chemically equivalent. This carbon is at a certain distance from this oxygen and from this methyl group, and this carbon has exactly the same geometry. Okay, there's a symmetry to the molecule there. So these two are chemically equivalent, as are these. So we'll only get 1, 2, 3, 4, 5 peaks in the carbon-13 spectrum. So the carbon-13 spectrum can only provide limited information in terms of determining structure or differentiating between isotopes. Differentiating between isomers. Carbon-13 cannot help you with determining which is of the isomers you have, is it carbon 2-methylphenol or 3-methylphenol, but it can tell you that you've got 4-methylphenol. So whilst it may not always be possible to use carbon-13 NMR to identify isomers, some can be identified using the spectrum. I strongly recommend at this point that you do some practice questions. If you have the OCR textbook, endorsed textbook, then on page 519 there's questions 1, 2 and 3 and the answers on page 590. But of course other textbooks will also have suitable questions.